All right, welcome everyone. Today we're going to start the last major discussion, major concept for our first semester calculus course. Okay, Math 20A here at MPC. So let's get going looking at the area under a curve, our kind of intro to what will become integration for us. Okay. All right, so here we go. Let me share my dot cam and we'll get going. All right. So kind of guiding our discussion, leading us into what we're going to start to call integration later. All right, we're going to look for the area under a curve, right? So our kind of concept or idea, we want to find the area under a curve, right? A function y equals f of x over a given interval. Okay, this closed interval from a to b. So we can generically, and we can put a solid function in later, but this concept is that suppose we have some function f of x or y equals f of x over this interval between a and b, okay? And again, we can talk about the function goes below. For now, this had an ease in discussion. We'll work in that first quadrant with positive values, so on, okay? But it could be any function over any interval, all right? And our question is going to be, well, what is that area enclosed going to be, okay? Or maybe later we can even trap some space between two curves. I know the function like g of x, and I want to find the area between those two curves. Okay, and physically, we can have what that area may represent for us, and we'll get into that as you go through. But just geometrically, let's think about trying to find this area. Okay, so how could we find this area, right? And so to find the area, we can begin by trying to approximate, right, estimate the area using kind of known shapes to fill in that space, that region, right? Because it's not a nice perfect rectangle, it's not a perfect triangle, circle. So I can't just kind of make my formula and say, okay, there's my area, right? With our function, our curve is going to be some kind of, right, gentle curve that's not going to follow necessarily a set known geometric figure. So let's start to do some estimations. And again, I'm going to kind of continue to redraw this. I know my function is not going to look perfect every time, but this kind of concept, right? And so one idea to make that estimate, let's just use one big rectangle, right? Depending on how high we're going to go, we can probably like that maximum point. Right? And so our area is approximately, roughly, right, the height times the width, length times width, whatever you want to call it, we can multiply. But in this case, since we are including space outside above the curve, this is going to be an over estimate, right? So maybe instead, what if we, again, I know my graph is altered a little bit, but this concept hopefully is clear. What if instead we look at that lower point, in this case, our area, approximately, let me use lowercase h, still the same width. But in this case, this is going to be an under a lower estimate, right? Because it's not including all the total area. So in between those values, the actual precise area would be in between, right? So we're going to think, well, how can we kind of get closer and closer, edge our way closer and closer to the precise area, okay? Right, so our precise area, actual area, is somewhere in between those quantities, right? From those two diagrams. How can we get closer and closer, right? Maybe hopefully that language kind of starts to bring in some of the calculus work we'll do later. Closer and closer to this precise area. The actual area under that curve. And so our initial discussion, use more. And since rectangles are easier to build up and find our formula for, we can do other shapes, triangles. In other calculations, you might see a trapezoid, okay, being used. But use more and more rectangles to fill in, to approximate that precise area, the precise region that we're trying to find the area for, okay? So I'm going to draw in a series of diagrams formulating this idea, this process. We can still work with our same function, right? Going between A to B. We tried one big rectangle. Well, maybe this time we can do two rectangles. Kind of get a little bit of the high part, a little bit of the low part. So maybe what we have over, what we have under, will kind of balance out to get us a better, pardon me, approximation. So in this case, our area is going to be those areas of our two rectangles put together. Okay? A little bit better approximation. Okay, well, that works. Considering, what if we use more rectangles still? Now, in this case, we did the part about splitting in half. Well, what if we split those in half again? So now, depending on how we organize it, I'm trying to make these as hopefully evenly spaced as possible. But now we can use these where, again, some have a little bit of overestimate, some have a little bit of underestimate, and maybe at the end, they'll kind of balance each other out. So in this case, we have 4 rectangles that we're using to make this approximation. And so this goes on and on, still taking that same function over our desired interval, but trying to utilize as many little rectangles as possible, right, to fill in. Okay, so kind of stacking these all up. And so our area is going to be the sum of all these little rectangles in the middle here, r sub I, like this little indexing, you know, the 10th, the 12th rectangle, all the way until we get to that very last rectangle to cover that space. Right, so we're adding up all these little areas and with a little bit of overestimate, underestimates, whatever it might be, because we're taking those little slivers thinner and thinner, we're going to be able to add those up, okay, and get this approximation. So this is this kind of concept starting through. Okay, so let's look at these areas of our rectangles and let's look at some of this notation. Okay, so with this idea, again, I know my graph is changing ever so slightly, but the concept remains the same. So now let's think about if we have one of those rectangles. This is my R sub I. So the area of one little rectangle. And R sub I. Okay. Well, the area for a rectangle, as I mentioned, was the height times our width, right? Length times width, whatever you want to call it. So in this case, for our area, well, how high is that rectangle going to be? Well, down here, this was our x-axis, right? And depending on where we take that component, up here, this is our f of x, our height. So precisely that, right? How tall we are is our function. The value of our function for whatever x point we're talking about. So our height, my f of x, and now what about this little bit of width, right? How far are we going to call that? If we go back to kind of our slope discussion, looking for the slope of our tangent line, those limits and whatnot, as we've gone through it to find the derivative, right? Okay, that width, we're going to call it this delta x, this little change in x, okay? How far are we going? This little bit, okay? That's going to be right, or little with little change in x, that little delta x. So for our width, blue, I guess, delta x. So depending on what we're using for our x coordinate, we can call it f of x sub I times the delta x. Right, and this is just our particular, our representative, our index, because depending on what x value we're at, we're going to get a different height, of course, when we plug into that function. So in total, is going to be, right, the sum of all of those rectangles that we're using to fill that region. And so in mathematics and our calculus discussion, that sum, we're going to use this sigma, this Greek symbol, to do that adding. So we're going to be taking the sum of all of those little rectangles, r sub I, the sum of all these rectangles, going from, letting I equal 1, the first rectangle, up until n. Okay? So this is the sum of all rectangles r sub I from I, that index equaling 1, to I equaling n at the very end. So when we had problems before, we might be adding from 1 to 4, 1 to 16, 1 to 100, whatever n we may choose, how many rectangles we want to split that space into. Okay? So this is this concept. So as we go through, in some of those written notes that I put up, probably in some of the slides that are available from the publisher, from the author, right? You'll see solid calculations with some known function, x squared plus 2x minus 1 something, right? Some curve that you can actually graph over some interval from 0 to 4, 0 to 1, whatever it might be. And you can imagine drawing and kind of putting those little rectangles in. We can choose that delta x to be as big or small as you want. These is just how much width we want in that little rectangle, right? So we can do like 1/10, 1/100 is really small, decimals, right? So we can fit more and more of those little rectangles in. So then where our calculus starts to show up, okay, to get that best estimate or approximation for that precise actual area, we want to use as many rectangles, that's why, as possible. Right? We saw just using 1 rectangle, 2 rectangles, 4 rectangles. Okay. we're going to try to fit as many as possible. So now this is where our calculus comes in. Because then for that area, it's going to be, right, I'm going to leave some space here, the sum of these different rectangles, right, those areas, and we can change this notation as we go along. But we want to use as many rectangles as possible. So what we're going to do, we're going to take this limit as n, the number of rectangles, goes to infinity, right, of that sum. All right, so the sum of those rectangles are 1, R2, R3, all the way to Rn. But now we're going to let n go to infinity. Infinitely many little rectangles trying to fill in that space. And adding those up, right? So that's where this limit notation brings in the work we saw. L'Hopital's rule, right? Taking the limits at infinity. Limits in general we talked about back in the first major discussion of the course, chapter 2, right? Going through, evaluating. And so as we go along, as we start to incorporate our function back into it, we have for those r sub I, right, our height times the width. For those little rectangles. That x sub I, right, just depend on what x we're using to get that particular height underneath our curve. Okay, and so this discussion, we call this our Riemann, right, for a mathematician that kind of initiated this process or kind of got famous for this process. That sigma is a summation. We call this the Riemann sum. And depending on where we would take that representative value, that x y, whether we do the right endpoints of these little intervals that we're breaking at, okay, or the left endpoints, midpoints, we can associate, okay? And so we start to work on is this following idea. We have our function, whatever that might look like, over that interval, and we start to create, I want to exaggerate the size here, our little rectangles. As we talked about, our height and width, the height, the value of our function at some representative value, x, okay? The width, this is where we're going to say we want to split up this interval into these little kind of equally sized parts. Okay, so we're going to call it this little delta x. Actually, I'm going to put it in blue. But that delta x we can actually get an expression for. If I want to take that interval and chop it up into equally sized parts, right? Whether it be 4 parts, 8 parts, 100 parts, n parts, We can do this b minus a all over n. Depending on how many rectangles we want, we take that full length, that distance, and divide into n parts, right? So this is going to create n equally sized or with rectangles. Okay, those bases, how wide they need to be. And then the height's given by that f sub xi. And so what we're going to start to build up into this next discussion is using these kind of expressions to replace and actually evaluating the limit. We're not going to really do too much labor in doing that. I'll kind of show that calculation, but truthfully, as long as we get this concept of ideas that we're taking all these little rectangles, compressing them, like making small, and using that to fill space, that's going to be the key concept to kind of sit and think about. The evaluation of this limit, we'll kind of go through with maybe some written examples. It might be helpful to do one on here just to see how the process is working, but just like derivatives before, right? We introduce a limit definition, but truthfully, we don't use it too much once we get used to the actual operation, okay? All right, so let me leave it at that. This area problem, I think in the lecture slides, some of the old written notes, there's some examples going through those set calculations with the function. So definitely take some time to look through the book, look through our written notes, provided slides to kind of identify with this concept, okay?